Hello, everyone, and welcome to this second annual conference of QTREC on zero emissions bus technologies and transit operations. My name is Conrad Cassier, and I am the ZEB, or Zero Emissions Bus Commercialization Team Lead here at QTREC, and it is my pleasure to welcome all of you to our panel here today. The panel is called Challenges and Opportunities for Electric Vehicles, and the speaker today on the panel is going to be Olivier Trecases, who is the Professor for Electrical and Computer Engineering at the University of Toronto. Before we begin, I would like to share that we have closed captions available in both French and English. You can enable this tool directly below the video stream. I am joining you today from Calgary in Alberta. Today, I'm joining you here from Calgary, and in the spirit of reconciliation, we acknowledge that we live, work, and play on the traditional territories of the Blackfoot Confederacy, Siksika, Kainai, Piikani, the Tsuut'ina, and Îyârhe Nakoda nations, the Métis Nation, Region 3, and all people who make their homes in the Treaty 7 region of southern Alberta. With that, I would like to hand over the microphone to our speaker to do his presentation. Thank you.
Okay, great. Thank you very much, Conrad, for the introduction, and thanks to QTREC for the invitation. So today I'm going to discuss some of the really exciting opportunities and challenges that have come up around electric vehicles. So I'm director of the U of T Electric Vehicle Research Center, and we have 10 faculty members covering the areas of electrical, computer, mechanical, and aerospace engineering. And we focus on the 6 core topics shown above. So enhanced energy management, next generation electric powertrain, energy storage, of course, is a central focus. Ubiquitous charging, so onboard, offboard charging, wireless charging. We look at advanced power modules and opportunities around EVs and particular second life applications. So one of the exciting opportunities is if you consider that, the more I work on electric vehicles, the more I see them as really gigantic batteries on wheels. And so if you think about that mobile energy source and you connect it back to the grid and you enable vehicle to grid, you can actually allow the integration of renewable energy, and you mitigate the natural variations in solar and wind generation. So at UTEP, we worked on high-density onboard bidirectional chargers, so we can send power back to the grid. We're leveraging wide bandgap semiconductors to shrink the size of these onboard chargers and increase the efficiency. And we can also enable power back from one vehicle to the next. So for example, if you had a bus that's in a blackout, that's been left with no energy, you could actually drive another bus and recharge it. Another opportunity is more advanced battery management systems. So this is a liquid-cooled module that we designed in UTEP. And we've actually developed some unique electronics inside the module that can send a perturbation signal and at variable frequencies and detect the response. So this is a way of determining the state of health of the batteries. So today's batteries are operated very conservatively because of the uncertainty around the maximum power limits, the amount of degradation. And this is really an exciting diagnostic tool to directly obtain the state of health at the cell level. Now, we're also looking into second life application of batteries. So this is a bit like a retirement home for batteries. So if we design the module from day one to have a seamless transition to second life, to transition, for example, from liquid cooling to air cooling, and we retain all of that information in the battery management system from the first life, and we can redeploy it in stationary applications. So once the battery has been degraded, for example, to 20%, we can redeploy to the grid, and that supports the integration of renewable, and also it supports the fast charge operation of EVs. And in this space, we've worked on algorithms that allow us to combine multiple batteries with different levels of degradation. And so if we optimize that power mix, then each module can contribute the optimum amount to the overall demand, and we can extend the life of all of these different modules. So the idea is that you would equalize the state of health over time and extend the overall lifetime of these modules. So this adds value to the EV ecosystem. Now, we're also very interested in autonomous vehicles, and wireless charging is an enabling technology for autonomous vehicles, because if no one is there to drive, obviously no one is there to plug it in. And so the Achilles heel for wireless charging has always been the low efficiency when you have a slight misalignment of the transmitter and receiver pads. So here we developed a unique architecture to charge from the rear of the vehicle, where we use an electromagnet to automatically align the transmitter to the receiver pad on the vehicle. So this would be a great option for commercial vehicles or even for electric buses. And we achieve over 90% efficiency. And we have this large tolerance to misalignment. And the pad is about 20 centimeters, or I think, 15 or 20 centimeters by 20 centimeters. And it is modular in 5 kilowatt units. Now, battery degradation, of course, is one of the major topics of concern for electrification. And so we've been looking into that. On the left, you can see the degradation curves for the Tesla Model S, for which we have a lot of data. And you can see that it's dropping to about, maybe 95% capacity around 100,000 kilometers. But there's a huge variation. And that depends on the driver behavior, the terrain, component mismatches, the climate where the vehicle is operating, and the strategy for electrothermal management. On the right, you have the Leaf, the Nissan Leaf degradation curves, and they're much steeper, and that's because the Leaf uses a cheaper air-cooled system, and so typically runs the battery much hotter than the Tesla. So if we look at a day in the life in an e-bus battery, and this data is provided by a company, Tessium in Toronto, that I started to really focus on telematics and EV energy analytics, we see the variations in power demand throughout the day. So we have very high acceleration and regenerative peaks, but the average power is relatively low. And so there's a continuous debate about what is the optimum lithium chemistry to satisfy this mission profile. And there's always trade-offs between the energy density, the power density, the cost, the degradation. Today, lithium iron phosphate seems to be the chemistry of the day, but that is always evolving. And so for fleet operators, for transit agencies, the major risk really is this uncertainty about the range that they will achieve for a certain battery size, and also the degradation. So this data was taken from one of our trials in Saskatoon, covering almost minus 40 degrees Celsius up to plus 30. So I can't think of many cities in the world that would experience that kind of extreme range in temperature. And you can see really each dot is a trip, and you can see the variation in efficiency in kilowatt hours per kilometer. So the blue star shows that the powertrain load is only 30% of the energy. So most of it is going to HVAC at such cold temperatures. Whereas at 20 degrees, 75 or 3/4 of the energy is actually going towards propulsion. So this is a financial risk, it's an operational risk, and it needs a lot of attention through telematics and analytics. We're also involved in the TTC trial, so you can see the Tessium IoT box here. We have an online portal that looks at all kinds of metrics around EV, looks at the acceleration histograms, the distribution of energy, and this really enables what's referred to as a digital twin, which is really a hot topic right now in EVs. And the idea is that beyond the feasibility stage, during the operation of these vehicles, that every vehicle would have an independent digital twin operating in the cloud, which is basically like a mathematical or a physics model of everything that's happening inside the vehicle. And it allows us to predict the energy consumption under any arbitrary profile. So any climate condition or any driving pattern. And this is something that we've really been working on over the past few years. So the digital twin model is actually tuned based on experimental data. So we have the experimental data, and We put that through the model and we compare the energy consumption. And in that way, we can have the predictive abilities, and then we can also tune the model parameters. So this shows, for example, on the left, real telematics data from Toronto and TTC. You can see the state of charge and the current drawn from the high voltage battery. And on the right, you can see the output from the digital twin. So not only is the state of charge matched, but also the peaks and valleys of the current on the battery. Now, one of the really exciting aspects of EVs, obviously, is regenerative braking, something that gasoline vehicles can never achieve. And one of our trials is on a coach bus here on Vancouver Island, going from Victoria to Nanaimo. You can see that it's going up and down the mountain. And this, for example, the telematics data, we're not just collecting position, we're collecting all kinds of waveform information, from all the subsystems in the EV. You can see that as it's going down the hill, it has this very long and sustained regen event. And so that is regenerating a significant amount of energy, which increases the range and also reduces the wear and the fatigue on the mechanical braking system. So it's fascinating to think, for example, that in 1 minute of regenerative braking on this coach bus on Vancouver Island, it's generating enough electricity to power a TV for 40 hours. And so that's a fascinating aspect of electric vehicles. So the second part of my presentation here is focused on a project that was funded by QTRIC in collaboration with Microgreen on investigating the electrification of the HVAC system in diesel buses. So the thinking here is that, as we try to reach the emissions targets, there are multiple approaches. So one of them is to, when we look at the existing fleet of diesel buses, and there are, of course, hundreds of thousands of them, we can, given that they still have a long useful life, we can modify them to have a hybrid drivetrain. We can do a full electric propulsion retrofit, which Gara Hay from Clean Power talked about, and I think it's a really exciting option, and we're working with him on that. Another alternative, which is maybe a lower hanging fruit and a bit cheaper, is just to electrify the climate control. So we keep the diesel powertrain, but how much GHG and fuel savings can be achieved by just electrifying the climate control. And that's what we looked at in this project. So first, we looked at, if you replace the typical 5 kilowatt hour lead acid battery in a diesel bus with lithium, you get more energy in the same volume. And what does that bring in terms of savings? So this battery typically today, is powering some pumps, some heating elements, compressors, and is recharged through the alternator that is loading the diesel engine. So instead of ripping out the powertrain, if you just replace that with lithium, what would happen? So we created this detailed model of the climate control system inside the bus and tried to calculate that load on the diesel engine. What does it produce in terms of GHG emissions? And if we electrified it, how much would we save? So we looked at, of course, it's only meaningful to look at on a long time period. So we looked at 3 different cities, Toronto, Los Angeles, and New York, because they have different climate, and 2 different speed profiles. So we had the central business district and the New York bus drive cycle. We also looked at the irradiance patterns in these cities. So that means basically the energy that's coming from the sun, and that's actually contributing to the HVAC load. So if sun is shining into the bus in the wintertime, it's helping to actually heat the interior cabin. And so we ran a very long simulation with these 3 different cities, 2 different drive cycles, to try to quantify the benefit of electrifying the HVAC system as a low-hanging fruit. So here you see some of the results for the 3 cities, so Toronto, LA, and New York versus the day in the year. And then different battery sizes. So as you increase the battery size, you have more energy to supply the HVAC system. But of course that costs more and it adds more weight to the bus. And so if we look at Toronto, for example, we see that, the larger the battery, the more savings we have. And of course there is a plateau, and we have more savings in the winter months because of course we're using more heating, and more savings in the summer as well. Or let's say in the peak of the summer. And then we tried to quantify the overall savings for the year versus the battery size. So here you can see the percentage emissions reduction versus the battery size. And for reference, a typical battery electric bus would have maybe 250 kilowatt hour or 300 kilowatt hour battery or above. So now we're talking about a much smaller and cheaper battery for the HVAC system. And you can see there is a point of diminishing returns. So if you increase the battery size beyond a certain point, you won't really get much emissions reduction while you're increasing the cost. And the potential for reducing emissions is obviously higher in cities that have a colder climate and using a lot of energy in the wintertime, like Toronto versus LA. And if you look at this chart, you can see the tons of GHG reduction per year per vehicle with the optimum battery size. So in Toronto, we were looking at roughly 75 to 100 kilowatt hours. And that would be maybe 11 to 17% or 17 tons per year, and about maybe 4,000 to 6,000 liters of fuel relative to 50,000 liters. So it's not nearly the same kind of savings and reduction as we would see with a full electrification of the powertrain, like ZEV Clean Power was promoting, but it's also cheaper, and it's an interesting intermediate alternative. So in conclusion, we looked at how to quantify really the fuel savings and GHG reduction potential for electrifying the HVAC system. Simply converting the lead acid battery to lithium just doesn't give you enough volume, enough energy to make a meaningful savings. So it has to be much larger than that, at least 10 times larger than the existing battery that's in diesel buses. And we saw that the savings was on the order of 8 to 17 tons per year per bus. And there are further improvements that can be made with charging multiple times a day, or with dynamically controlling the HVAC system to improve the efficiency of the diesel engine. And of course, in the first part of my presentation, I highlighted some of the exciting innovation opportunities for zero-emission vehicles, and also tried to showcase the importance of telematics and of accurate model, and really the potential of digital twinning to mitigate the risk of electrifying both passenger vehicles and transit vehicles. So with that, I will end the talk, and I want to thank everyone for attending. I see we have 100 participants, so that's very exciting, and I look forward to the questions.
All right, thank you very much, Olivier. I really enjoyed that presentation. And for me personally, I really enjoyed what you said about the regenerative braking and the TV. I think that just goes to show how interesting all these technologies really are. There are some questions, and I think I'll pose the first one to you. You mentioned telematics. Now, how mainstream is telematics data for risk mitigation in Canada? And what needs to be done to scale this up further?
Well, it's a great question, and I think some people have said data is the new oil, right? So it's hard to overstate the importance of data, especially when we talk about electric vehicles and risk mitigation. So telematics is a bit of a catch-all, but there are obviously a whole spectrum of different technology solutions. And right now, telematics are very widely deployed in both diesel and electric vehicles, but in many cases, they're very rudimentary. So they're just looking at, positioning and some very crude metrics, whereas, at Tessium, we really saw that gap and the need to go much deeper into telematics. So we are collecting, potentially dozens of parameters multiple times per second, and we're recreating waveforms of current, voltage, and all the other, and temperature within the vehicle. So we can put AI on that. We can detect unusual events, and through digital twinning, we can actually predict when failures might happen, so we can detect drift in certain parameters within the vehicle. So I think telematics is widely deployed, but we need to take it to the next level, and hopefully we can do that with local technology, particularly in Canada, where we have very unique climate or let's say weather conditions that make forecasting of energy consumption that much more important. Think about Saskatoon running at minus 35 degrees. That's really a challenging space for EVs.
It really is. Olivier, would you mind turning your camera on, please? I think it's still on. There we go. Then in a related question, has your research and modeling shown effective ways for transit agencies and our city councils to work together to bring down EV costs and the charger costs? What's your opinion on that one?
Well, it's a major concern. Obviously, the infrastructure beyond the vehicle itself, and so there are questions about the impacts to the grid, and I think that picture is emerging. More so in the last few years. I think some of the concerns have been overstated, and we need to make this work. Obviously, we're facing existential problems in terms of dealing with climate change, so we need to make it work. And there are a number of solutions. So stationary batteries to support fast charging of vehicles is an obvious one, and there are companies like eCamion and others that are doing great work in that space. Redeploying depleted EV batteries to support other EVs in stationary mode. That's really interesting. And also just smart charging.
Yeah.
What's the interesting thing about EVs? That they are controllable in terms of charge power, and we're involved in that as well. So, using the optimum charge power to be just in time and to have really the minimum impact on the grid. And then if we talk about vehicle to grid and the economic benefits that can deliver to a utility in terms of reducing, new generation and reducing capacity or transmission upgrades and so on. So there's all kinds of technology solutions to improve the business case for EVs.
Yeah, that is fascinating. On a personal level, I really enjoy the topic of smart charging. I hope we can at some point speak about that a bit more thoroughly. And in relation to what you've said there, as Canada ramps up its emissions reductions plans, and with the announcement that we heard on Tuesday as well coming from the federal government, how has your research in this area given any idea about the stability of the power grid, especially as we look at more zero emissions vehicles coming into play, which will affect the grid? Anything you have to say about that?
Sure. I'm more involved in power electronics and vehicle subsystems and IoT and so on than the wider, let's say, topic of grid stability. But I would say that both smart charging and deploying stationary batteries to decouple these fast chargers from the grid is extremely promising. And it's really a beautiful story around electric vehicles, renewable energy, working in harmony, because of course, electric vehicles provide the storage that when they're not in use through technologies like vehicle to grid can help support, fluctuation of generation and renewables. So I think, the movement towards smart grid, towards decentralized control, having stationary batteries and smart charging together can go very far to alleviate some of the concerns about the grid. In terms of the overall capacity, we need to increase it, obviously, and it's on the order of, I think 150 terawatt hours or something is the number that's been thrown out there for passenger vehicles. It's not as massive relative to what we are generating today as some might think. And as I said, we have to solve this problem. It's not an option, and I think we will.
That is great. We are running a bit short on time. There are some other questions which I think are quite pertinent about V2X, but we can take that perhaps into our networking session later on. So I would just like to, in closing, thank all our sponsors, because without our sponsors, putting on these panels and this conference would not be possible. So a very special thank you to all of our sponsors and all participants. Thank you for all our panelists, in this case, Olivier, and to our audience who joined us this morning. If you would like to continue the dialogue, please do join us at our virtual networking, which takes place at 3:15 Eastern Time 3:30 Eastern Time, my mistake. And if you missed it, I'm also thrilled to announce, which we also shared yesterday, that QTRIC has been named the National Planning Service for Infrastructure Canada's Zero Emission Transit Fund. We are excited to support transit agencies and municipalities to plan their way to a zero-emission transit fleet. To learn more, please contact us via email, and please do pay our website a visit as well. Thanks again for your participation, everybody, and we look forward to seeing you in our next session. Thank you very much. Thanks, Olivier.
Thank you, Comrade.